probably you may start. So our speaker for today is Kehe Zhu from University of Albany and Shantou University in China. And the title is Sarason's Ha-plitz product problem. Please, Kehe.
All right, thank you, Nikolai. It's very nice to be giving a talk for your group. I'm going to talk about a problem that Sarason raised about 20-25 years ago. Initially, Sarason raised the problem for Toeplitz operators on the Hardy space and also the Bergman space. But obviously, the problem also makes sense for the Fock space. So I will consider all these three cases today.
Mm-hmm.
Let me begin with the spaces. I assume there are some graduate students over here, so I will try to give a little more detail. So C will be the complex plane, and D is the unit disk, and then T will be the unit circle. And in each one of the situations, you can define a L2 space, and then inside the L2 space, there will be an analytic subspace. Okay, so on the unit circle, the L2 space is the usual L2, and you use occurrence measure. And inside L2, you can define the so-called Hardy space, H2. And the easiest way is to expand a function in L2 into a Fourier series. And if all the Fourier coefficients for k less than 0 is equal to 0, then the function is in the Hardy space. So
basically, it traces on the unit circle of analytic function.
Yes, and then when you extend such a function inside, then you get an analytic function.
Yeah.
So that's the, that's one way to define the Hardy space. There are other ways. And in this particular setup, then you can think of the functions in the Hardy space as like spaces living on the circle.
Mm-hmm.
I will need to use L2 of the circle. And then the second space I'm going to use is the Bergman space. The definition is very easy. You simply, in this case, I just consider the disk, the area measure dA, and you look at the usual L2 space, and then you look at all the analytic functions inside L2. So it's L2 intersection with HD. HD
Mm-hmm.
is of all analytic functions. So this is what you call the Bergman space. So once again, the Hardy space lives on the circle, the Bergman space lives on the disk. And then on the complex plane, I'm going to define another space. So on the complex plane C, I will consider a measure. My notation over here is d lambda. It's the area measure with the weight. The weight over here is usually called as a Gaussian weight. And this is a rapidly decreasing weight. So certainly it's after the weight, this is a relatively small measure. And it's a measure over here, it's called as a Gaussian measure. You look at the L2 space of the plane with respect to the Gaussian measure, and then you look at all the entire functions inside L2. So H of C is the space of all entire functions on the complex plane. And so the intersection over here, I denote by F2, and this is what I call the Fock space. So once again, in all these three cases, you're going to have a L2 space, and then inside L2, there is going to be an analytic subspace. So, no matter what context you have, I'll just use L2 to denote the L2 space. And then inside the L2, there is an analytic subspace, which I denote by H. And then I'm going to have a orthogonal projection from the big L2 space to the subspace of analytic functions. In the case of the circle, it's usually called the Ziegel projection. In the case of the Bergman space, it's the Bergman projection. And then on the plane, the case of the Fock space, I don't think there's a name, but obviously there is such a projection.
Yeah, I think it's Bergman projection.
Bergman projection, sounds good. Okay, and then in each one of the three cases, if you are given a bounded function, not necessarily analytic, any bounded function, say on the circle, on the disk, on the plane, then you can define what is called a Toeplitz operator T phi. And the definition is is you simply multiply a function f from the analytic space by the function phi. What you get is no longer analytic, but it's still in L2. Then you use the projection to take this product back into the analytic subspace. So this will define a operator on the space H. You can also define a related operator. So the TFI is called the Toeplitz operator. And then you can also define a somewhat related operator called the Hankel operator. Instead of using the projection onto the analytic subspace, you use the projection onto the complement. I mean, the orthogonal complement of the analytic subspace, and then what you get is the Hankel operator.
Basically, it's identity minus difference.
Yeah, it's identity minus P. So the main difference over here is the Toeplitz operator maps H back into H, and then the Hankel operator maps H to the orthogonal complement of H. Okay, so they're called Toeplitz and Hankel operators. And because everybody who studies this kind of operators, they always study the two types of operators together. And so people sometimes will combine them and say that you are looking at Ha-plitz operators. Hankel, Toeplitz together is Ha-plitz. Okay. In each of the three cases, the orthogonal projection is actually an integral operator. And the integral kernel you can actually compute. In the case of the Hardy space, the kernel is given by this. And in the case of the Bergman space, it's the ordinary Bergman kernel. And in the case of the Fock space, it is the linear exponential kernel. And one of the nice features when you think of the projection as an integral operator is that you can then extend the domain of the projection to a larger space, a space larger than L2. Because initially the P is defined on L2, but if you write P as an integral operator, then P of F can be actually defined for functions F, not necessarily in L2. And with this extension of the domain of the P, you can also define Toeplitz and Hankel operators for functions phi that are not necessarily bounded. Okay, so it's a technical adjustment over here. Initially, the P is only defined on L2, but using the integral formula, you can extend its domain to something larger than L2. And then you can define Hankel Toeplitz operators with unbounded symbol functions. And in each of the three cases, you can easily come up with unbounded functions phi and xi such that the Toeplitz product is a bounded operator. That is always possible. If you only look at an individual Toeplitz operator, in the case of the Hardy space, then the Toeplitz operator is bounded if and only if the function is bounded. But if you look at this product, it is possible that you have a certain cancellation going on. And then it is possible to construct unbounded functions phi and xi such that the product over here is bounded. So Sarason's problem is this. Again, Sarason initially posed the problem for the Hardy space and the Bergman space. He was asking to characterize all analytic functions phi and xi, okay, such that this particular product of two Toeplitz operators is bounded. You want to look at this very carefully. The order of multiplication is important. So phi and xi are both analytic. And on the right-hand side, you're going to have a conjugate analytic symbol. And on the left side, you have an analytic symbol.
Kehe, may I ask you?
Yeah.
Do you remember motivation of Sarason to this problem?
Yeah, it's a good question. I never figured out the motivation. I don't know. I mean, I also asked this question myself, but unfortunately, I studied this question after Sarason passed away, so I don't really know. My guess is, because I remember the question was raised in around 1994. Around that time, Sarason was doing research on exposed points of H1 papers, and he did that like for several years. Most likely, it's related to that research program about points and exposed points. but I don't know.
Okay.
Yeah,
Sorry.
anyway, so the question was actually asked very formally. There is a Springer a problem book. I'm sure Nikolai knows this book.
Yeah.
You probably have problems in the book also.
No.
But I have like a couple of question problems in the book. It's a very nice book, especially for graduate students. I mean, if you're looking for problems or just for fun, I mean, you should get a copy of the book. There are actually 3 versions of the book. The first edition of the book, I remember there are 199 problems. And then there was a second edition with more problems. And then later on, there was another edition. And I think the most recent version has probably over 300 problems in the book. Problems. So this is the original first version of the book. You can find the book you can find the problem in the book. So anyway, so coming back to the problem, you want to describe all the analytic functions phi and xi such that this particular product is bounded. And again, the order of multiplication is important. You want to put the conjugate analytic function on the right and the analytic one on the left, because if you switch the order of multiplication, then the two Toeplitz product, the product will become a single Toeplitz operator. So, but in this particular order, you cannot combine them into a single Toeplitz operator. And it turns out, again, the motivation is important, but I don't know what it is. It turns out it's a very delicate question. If you, the first time you see this, you wonder, what is this all about? But it turns out it's a very delicate question, and it's actually a very difficult question. The problem is still open for the Hardy space and for the Bergman space. It's still an open problem. But what I want to report today is that the question can be completely answered in the case of the Fock space. Obviously, it's exactly the same question. You can just add the Fock space and you can ask the same question. And it turns out for the Fock space, the answer is much nicer. So clearly, I just want to emphasize that the problem clearly makes sense for the Fock space also. Now, when Sarason posted this problem, he also made a conjecture. So his conjecture in the same book, in the Springer problem book, he made a conjecture. His conjecture was that this product of two Toeplitz operators is bounded if and only if this product has two functions in terms of the so-called Berenson transform. In each case, you can define the Berenson transform. In the case of the Hardy space, the Berenson transform is the usual Poisson transform. Then for the Bergman space and the Fock space, the Berenson transform is a very useful tool to study operator theory. So his conjecture was that this operator is bounded if and only if this product of two functions is bounded. And he conjectured that this is true for both the Hardy space and the Bergman space. Not only he provided a conjecture, he also proved one direction of the conjecture. It's a half-page proof. So what Sarason actually proved was that if the operator over here is bounded, then the function will be bounded. So he had proof for both the Hardy space and the Bergman space. The proof is not long. I remember it's half a page. I actually checked the proof. The proof is not difficult, but it's not trivial either. You need to have a very good idea of what you're trying to do, and he had a very nice argument. So, I mean, if you're interested, you can check out the book and take a look at the proof. And then I checked the proof. His proof does not work for the Fock space. The proof only works for the Hardy space and the Bergman space. And later on, it turns out you're going to see that his proof, it doesn't, not only his proof does not work for the Fock space, actually this direction is wrong. The proof, now we know that the proof cannot be modified in any way to work for the Fock space. There is a good difference between the two settings. Anyway, so this is the background for the problem. You had the problem that it's still an open problem, and then you also had a conjecture. Now the conjecture turns out to be wrong for the Hardy space and the Bergman space. For the Hardy space, again, remember, Sarason also had a proof for one direction. If the operator is bounded, then this function is bounded. So that direction is proved. And so when I say the conjecture is wrong, I'm saying the other direction is wrong. In the case of the Hardy space, in a paper by Nazarov in 1997, the paper was posted in the archives. Online, you can find the paper, but I don't think the paper is ever published. So Nazarov actually came up with a counterexample in the case of the Hardy space, where he can show that you can come up with two analytic functions on the circle such that this function is bounded, but the Toeplitz product is not bounded. The conjecture is wrong. It is wrong for the Hardy space. And then in 2013, the conjecture was also disproved for the Bergman space. And this is in the paper by Alleman, Pott, and Ruggiero. And this paper is already published, so it's available. And so they construct a example of two functions, both analytic on the unit disk, such that the function over here, in terms of the Bergman version of the Bergman transform, such that this is bounded, but the Toeplitz product is unbounded. So the conjecture is now completely resolved. We know that it's
Kehe, can you say in 2 words what are these functions? What's specific for them?
You mean the counterexamples they constructed?
For Bergman space.
No, it's impossible to describe in like 2 words. It's a very technical construction. It's not easy.
I see. Okay, great.
Yeah.
Thank you.
Yeah. So yeah, if you're looking for like elementary examples, there's no way.
Okay.
And the way they constructed this 2 counterexamples is using a connection to a very classical harmonic analysis technique. So it turns out the Sarason's problem is equivalent actually to a certain 2-weight estimate for the risk projection in the case of the Hardy space, and also for the Bergman projection in the case of the Bergman space. And the way they constructed the counterexamples is using this connection, and I'll show you what the exact connection is. So Sarason's problem, the problem is equivalent to this. So in the space, it's a little easier to describe. You're given 2 analytic functions, f and g, and then you look at 2 weighted measures like this. And then you have like 2 L2 spaces with different weights. And the problem is equivalent to exactly when this projection is going to be a bounded operator from this space to this space. And so in harmonic analysis, people studied, this is what you call 2-weight problems. There are 2 different weights. And
so actually it's not projection, it's like integral operator.
You think of the projection as an integral operator.
Yeah.
You want to study it actually. Yes. Yeah. And so there's a similar description for the Hardy space, and there's also a similar description for the Fock space. And so the construction of the counterexamples is based on this equivalence techniques from harmonic analysis. But the 2-weight estimates in harmonic analysis is well known. It's well known to be a very difficult question in general. In this case, the weights are somewhat special. They're like a absolutely continuous. Still, the problem is highly non-trivial. So that's how they constructed the counterexamples. Now, for the remember for the original problem, the Hardy space and the Bergman space, Sarason had a conjecture and he proved 1/2 of the conjecture, and by now we know that the other half of the conjecture is false. And we know that Sarason's original projection for that half does not work for the Fock space. Now, before the counterexamples came about, there were actually some earlier work about the problem. Remember, the earlier conjecture is this. One direction is known, and then before the counterexamples were constructed, there were actually some earlier work, which I think is interesting, for both the Hardy and the Bergman space. Most well-known partial result in the other direction, okay? By now we know that the other direction is not true, but if you are willing to increase the 2 to 2 plus epsilon, this function is bounded, then it turns out the operator will be bounded. And this result is actually very well known I think in the late 1990s, early 2000. I don't remember exactly who did this, but bottom line is if you're willing to increase the exponent over here a little bit, then you can actually go back. Okay, so
there exists epsilon or for each epsilon greater than.
Yeah, actually it's for epsilon bigger than a certain constant. So the notation epsilon.
Oh, yeah.
Yeah,
okay.
so yeah, maybe you should not use epsilon. It should be like 2 plus a certain number that is a large enough number.
Okay, great. Sure.
Yeah. So that is the story for the Hardy space and the Bergman space, and then I'll stop over here for those 2 cases, because for those 2 cases, this is it. Nobody knows anything more. So Sarason's original problem is still open. You don't know exactly when this Toeplitz product is bounded. Again, I know that several people have worked on this problem, but as of now, the problem is still open, although the conjecture is false, but you can still ask the problem and there's no answer as of now. So in the rest of my talk today, I'll just focus on the Fock space, and then it turns out in the case of the Fock space, the situation is completely different. And the usual, the main feature in the case of the Fock space is that it turns out what is easy in the case of the Hardy space and the Bergman space is going to be difficult for the Fock space, and what is difficult for the Hardy and the Bergman space will be easier for the Fock space. It's the other way around when you look at the 2 implications. So in classical 2 cases, this direction is easier. Going from operator to function is easier. The other direction is harder, it's not true. And it turns out in the case of the Fock space, the easy direction will become the difficult direction and vice versa. All right, so let me just first show you the one of the results first. In 2014, there was a several complex variable conference in Korea. I went there, I gave a talk, and then after my talk, a graduate student came up to me and told me that he was working on Sarason's problem. And at that time, I had no idea what Sarason's problem was. So he explained the problem to me, and he said that the problem makes sense for the Fock space because at that time, I just published a book on the Fock space, so he thought I should know something about the Fock space. He showed me what the problem is, and then I started looking at the problem, and then after a few weeks, we worked out a complete solution. So for the case of the Fock space, if you are given 2 entire functions, it's always a good idea to start with the functions inside the Fock space. Otherwise, the Toeplitz operator will not even be densely defined. Okay, so you start out with 2 functions in the Fock space entire, and then it turns out on the case of the Fock space, this product is bounded if and only if the function f is a constant times a linear exponential function, and g is also a constant times a linear exponential function, and the cz over here, and it's going to be the minus cz over there. In other words, there will be a cancellation if you try to multiply f and g. So in this particular case, it turns out not only you can describe exactly when this product is bounded, you know exactly what the functions will have to be. They will have to look like this.
Mm-hmm.
And then after we figured this out, then we went back to Sarason's conjecture, and then we realized that this operator is bounded if and only if this function is bounded. It is because in this case, we can actually compute the Barrowson transform, and then it turns out in the case of the Fock space, if you want something like this to be bounded, you're gonna get the same condition. F will have to look like this, and the G will have to look like this, and there's no other way for this function to be bounded. And therefore, as a corollary, we see that in the case of the Fock space, Sarason's conjecture is actually true. So that's why I say that the conjecture, although we don't know what the motivation is, we see that the conjecture is really very precise.
Mm-hmm.
It is exactly true for the Fock space. For the Hardy space and the Bergman space, it's off a little bit, but over here it is exactly true. The proof for this theorem, there are two main ingredients in the proof. Number one is a very classical result in complex analysis, the so-called Lovier's theorem. And that says that on the plane, there's no bounded analytic function. There's no bounded harmonic function other than constants. So that is kind of rigidity for the complex plane. And that explains why you can do this on the complex plane, but you cannot do it like on the disk. So that's one thing. Another thing is the Weil unitary operators. I'll tell you what they are, and it turns out to solve this problem, you need to use the Weil unitary operators. With the two ingredients, we can prove this. I'll show you one direction. So the Weil integral operators came from a certain group action. When you do analysis on the disk, of course, you use the Mobius group. And on the complex plane, there is a similar group, okay? For the Mobius group, I mean, there are two types of Mobius maps. There are the symmetries, and then there are the rotations on the disk. On the complex plane, if you want to move the complex plane around, the right group is called the Heisenberg group, and very similar to the Mobius group. The Mobius group on the disk is the disk times the circle as a set. And the Heisenberg group is similar. As a set, it is the complex plane times the real line. And the group operation, you don't really have to pay attention over here. I'm sure most people have heard the term Heisenberg group. If you are just wondering, there is the group action. In the complex direction, it's just addition. And in the real direction, it's a twisted kind of operation. Not only you want to add S and T, you want to modify it according to the complex part. This is a group that has been studied in harmonic analysis for many, many years. Again, the right way to think about this in this context is to compare with the Mobius group. The Mobius group is really the disk times the circle, and every Mobius map can be written as something like this. Everyone who has done any analysis on the disk will recognize the phi A that I usually use. And then there's also rotation. In the case of the complex plane, the phi A, the analog of the phi A will be just translation. So I'm going to by tau A over here is just translation, and then you also have rotation for the complex plane. So on the unit disk, usually you don't really pay much attention to the rotations. To give you something trivial, you focus on the phi A, and similar on the complex plane, you focus on the translations. For example, every translation will induce a unitary operator, which is usually called the Weil unitary operator. For any fixed complex number A, you look at this translation. Because the measure you use for the Fock space is not the area measure, it's the weighted area measure. And therefore, in order to preserve the norm, the Jacobian. And the Jacobian is exactly the normalized reproducing kernel for the Fock space. Something similar, you can define this like for the Bergman space, for the Hardy space. So it's rotation modified by the Jacobian, the complex Jacobian, which is the normalized reproducing kernel. And then each one of this is a unitary operator. It turns out they're very old objects in quantum mechanics. They're called wild integral operators. And the connection between the wild operators and the Heisenberg group is, of course, just if you map AT to EIT times WA, this is actually a unitary representation of the Heisenberg group. Anyway, so you just realize that for every translation, there is a unitary operator. Okay. Mm-hmm. And then if I want to show you one direction of the earlier theorem, you assume that, say, forget about the constants in front of f and g. If you just take f to be a function like this and g to be a function like this, if you calculate the product, it turns out to be a constant times a unitary operator. And you can actually do this computation in detail. You first calculate the Toeplitz operator TG bar. And again, you don't have to go through the details. You should trust me. I've done this many, many times. The Toeplitz operator is exactly just a translation. And then if you multiply the f back, the f is like a reproducing kernel, and with a modification of this constant, it's going to be the normalized reproducing kernel. So if you multiply TF from the left, it's going to be something like this. And so it's exactly this constant times the wild unitary operator. And then you realize that this operator is not only bounded in this case, it's actually constant times the unitary. So it's in a very strong sense. In particular, this tells us that if you get a bounded product in this context, there's no way for the product to be compact. The unitary operator times a constant, times a positive constant. So it's a very, very nice bounded operator for this product. And so this direction is easy, and the difficult direction is the other direction. When the product TF-TG bar is bounded, you want to show that F must be more or less this, and G is more or less this. For that direction, I'm going to skip the details. Not too difficult, but again, you have to use several results from complex analysis. The Wills theorem is one of the ingredients, and then there are some other things you need to use. Okay, so again, I mentioned that this product, although it can be bounded, it can never be compact because it's a positive constant times a wild operator times a unitary operator. The only way to make this product a compact operator is when one of f and g is 0. The calculations we did over here also has another interesting implication. If you look at two functions that are related like this, if you look at f like this and g like this, again, if you take f times g is equal to 1, but this time the Toeplitz product over here by our theorem is going to be unbounded because f and g are not linear exponential. But you can actually compute the Barrowson transform of this product operator. And when you compute the Barrowson transform, it comes to fz times gz bar. And if you take the modulus of this, then the bar, you don't need the bar, and then f times g will be 1. I mentioned this example, it is because this is an example of an operator which is unbounded, but its Barrowson transform is bounded. For used the Barrowson transform is always a tricky question to know exactly when the boundedness of the operator and the boundedness of the Barrowson transform will be the same. And so this simple example shows that this is usually not true. Okay, so that's the Sarason's problem for Toeplitz product in all the three cases. For the Hardy space and the Bergman space, the conjecture was wrong. And for the Fock space, the conjecture is right. And we can also do more. We can know exactly f and g will have to be. And then in the remaining few minutes over here, I want to mention that there are two other very natural companion problems. Instead of looking at the Toeplitz product, you can also look at the product of two Hankel operators, and you can also look at the product of a Toeplitz operator and a Hankel operator. Okay, so I'll start with the Hankel product. The most natural product is this. You have Hg bar on the right-hand side, and then you have H of F bar conjugate I-joint on the left. Now, when F and G are analytic, you have to use the bar for both operators. Otherwise, the Hankel operator will be 0. Okay, so you have to put bar on both for both operators, but then you put the conjugate on the left, and then this way the product will be defined on the analytic space, and then the range is also the analytic space. So this particular construction will give you an operator on H2, on A2, on F2. Domain is this, and also range is the same when you do this. So you can also ask for what analytic functions F and G this product is bounded, and you can ask this question for all the 3 cases. You can also ask a similar question. You can ask the question for a mixed product. I have a Toeplitz operator and a Hankel operator over here. Now this time, of course, the operator will map the analytic space to the orthogonal complement because I have an operator on the left. And now, I mentioned 2 companion results over here, but obviously there are some other types of products you can consider. For example, over here, I can put Hankel operator in the first case, I can. There are several ways you can switch the product around and make the problem still make sense.
For example, consider adjoint operators. You feel more comfortable together.
Yeah, you want to use the Hankel Toeplitz operators and their I-joints to do the combinations. So I look at 2 particular combinations over here. The reason I look at this 2 is because I have results. And the other products I have not considered. And I do not have any plans to continue. So if any students want to continue, you can definitely try this kind of problems. Okay, I want to show you that in these 2 particular combinations, you can get very nice results. And it turns out problems like this also have been already been studied in the late 1990s and early 2000s. Bottom line is that if you ask questions like this, they're still wide open for the Hardy space and for the Bergman space. And in the last 2 or 3 years, together with one of my colleagues at Vanderbilt University and 2 students in China, we worked out solutions to these 2 problems. And the answers turned out to be very nice. So I want to show you.
Vanderbilt is the Chao Zheng?
Yes, they're Chao, yes. Yeah. So let's see. And in the late 1990s, actually, the Chao Zheng and also Carol Strothoff, probably remember the name. The 2 of them actually worked on these 2 problems for several years, although they did not mention the connection to Sarason's product problem. But obviously, it's all in the same spirit. So they already had like some partial results like 20 years ago, and at that time they were only looking at the Hardy space and the Bergman space, and they could do like one direction and they could not do the other direction after a few years to start. And then a few years ago we picked up the Fox space case, and then we worked out some cases. Okay, so first I want to mention that the problem is non-trivial. Okay, for the Fox space. You can come up with, in each of the 3 cases, you can certainly come up with examples of unbounded simple functions such that the kind of products you're looking at will be a bounded operator. And then the conjecture will also be very natural. In the case of the Toeplitz product, Sarason had a conjecture in terms of a product of 2 functions. Each function is the Bersin transform. And for the Hardy product, the conjecture was already made in the 1990s, late 1990s, and its conjecture was this. If FG are both analytic, then this Hankel product is bounded if and only if this product of two functions is bounded. Again, if you have worked on problems about Hankel operators, you probably recognize something like this. Something like this certainly shows up in my book, in my first book, many places. Every time you study Hankel operators, a function like this will show up. This is related to mean oscillation. So the conjecture at that time was that this product is bounded if and only if this product of two functions is bounded. Again, in the late 1990s, Joseph and then they proved that one direction is actually true. If the operator over here is bounded, then this function is bounded for both the Hardy space and the Bergman space. And for the Bergman space, you can actually do this for Bergman space on bounded symmetric domains. One direction is true. Very similar to Sarason's original argument. And the other direction, they worked on it for several years and they could not do it. And the problem is still open. So it's still an open, there's no counterexample, there's no proof. The difficult direction for these two spaces is whether or not the boundedness of this function will give you the boundedness of the operator, and its answer is still unknown. There's no proof and there are no counterexamples. Again, in the late 1990s, they had some partial results. I'm not going to mention the partial results. But one direction is true, the other direction is unknown. Now, so obviously you can also ask the same question for the Fock space, and you wonder what's going to be true, and you can make the same conjecture. The conjecture is still this: the Hankel product is bounded on the Fock space if and only if this function is bounded, because on the Fock space you can also define the Bayesian transform. Okay. Now, when we first started this like 2 or 3 years ago, the intuition was that in the case of the Toeplitz product problem, one direction was easy. The boundedness of the operator implies the boundedness of the function. So we wonder if that's going to be true also in the Hankel product problem. And then it turns out it's not so. It's exactly the opposite. Like I mentioned earlier, what was easy for the Hardy space and Bergman space turns out to be difficult for the Fock space. And in the case of the Hankel product problem, the other direction, the easy direction, was actually wrong. So the surprise was, we discovered the surprise in 2018. So again, let me describe what the surprise was. Again, in terms of this product function, okay? The conjecture was that the operator is bounded if and only if this is bounded. On H2 and A2, one direction is true. If the operator is bounded, then this function is bounded. And then we realized in 2018 that this is actually false for the Fock space. In other words, for the Fock space, there are counterexamples. You can construct examples FG such that the operator is bounded, but the function is not bounded. That's one surprise. And another surprise was that the difficult direction for H2 and A2, the difficult direction for H2 A2 is still unknown. In other words, if this function is bounded, you don't know if this operator is going to be bounded on H2 A2. And then we realized that that difficult direction is actually true for the Fock space. And not only that, we can describe exactly when this function is bounded in the case of the Fock space. For the Fock space, we still do not know exactly when this operator is bounded, but we know for sure exactly when this function will be bounded. We have a complete description. The description is this. So forget about the operators, just focus on this function first. Okay, you have two functions f and g in the Fock space, and you look at this product in terms of the Gaussian transforms. Then we know exactly when this will be a bounded function. This is bounded if and only if one of the several cases is true. First case is the trivial case. That's when one of f and g is constant. Because if f or g is constant, this is going to be 0, obvious.
Mm-hmm.
The trivial case, and then there is a semi-trivial case. It's when both f and g are linear polynomials. So f is az plus b and g is cz plus d. When both f and g are linear polynomials, then it turns out each factor will be a constant, although not 0, but it's going to be a constant. So that's going to be the semi-obvious case. And then the non-trivial case is when f is given by this formula and g is given by this formula. And in all the three cases, we can actually compute this. And it turns out the only way for this to be bounded is when you have fg occurring in one of these three cases. So we know when this is bounded. And since we figured out exactly when this is bounded, we can then go back and check. In each case, we can check that the corresponding Hankel product is bounded. Then we can compute. The trivial case, the Hankel operator will be 0. The middle case, the Hankel operators will be non-trivial but bounded, that is known. And then the last case, you have to do some analysis to show that the Hankel product is bounded. So in this case, if this function is bounded, we know the Hankel product is bounded. And in the other direction, we actually came up with a counterexample. Our counterexample is that we can construct functions f and g such that this Hankel product is not only bounded, but is actually almost, it's 0 almost everywhere. The Hankel product is 0, and then this function is now not bounded. And for this, the example is not too difficult. Once you write it down, it's actually relatively easy to verify. What we had to do was we have to use like on the complex plane, there are many, many complex periodic functions. Mm-hmm. And you use a clever use of those periodic functions, you can come up with examples so that this is actually 0 and this is unbounded. So that's the Hankel product problem. To summarize, in the case of the Hardy space and Bergman space, the problem is still open. The conjecture is not true. The conjecture is also open. One direction is known, the other direction unknown. And for the Fock space, the conjecture now is known to be false. One direction is true and the other direction is and the level of difficulty is exactly opposite to the case on the disk and on the circle. And then so yeah, okay, I already said this. The other direction can actually have counterexamples where the operator is 0, but this function is unbounded. Okay. Okay, so that's the story for the Hankel product. And then I want to talk about the mixed product. You have a Toeplitz operator and a Hankel operator, and you want to know exactly when this product is a bounded operator. And again, the conjecture is, by now, is standard. So the conjecture will be this. And again, this conjecture was already known in the late 1990s. This product of a mixed product to be bounded operator, then you want this function to be bounded. Corresponding to the Hankel, you want this difference, and corresponding to the Toeplitz, you want just g squared. First time you see something like this, notice that in the first term is when you first take modulus f squared and then you take the Bergson transform. The second term is when you take the Bergson transform first and then you take the modulus squared. It's similar to like conditional expectation. It is a very well-known construction in mathematics. This is always non-negative. Okay, so the conjecture is this. And again, this conjecture was studied in the late 1990s. One direction was done, the other direction still open, and there's no counterexample, no proof for H2 and A2. So what I want to talk about is what happens in the case of the Fock space. Okay, it turns out for the Fock space, I mean, before you have the result, if you make guesses at this point, is actually unclear. For the Toeplitz product on the Fock space, you have a very nice answer. For the Hankel product, the conjecture is false, it's not true. And you may wonder what's going to happen when you look at a mixed product like this. Is the conjecture going to be true or false? And it turns out the conjecture is actually true. So the result is this. Again, it's the other Z is the Chao Zing, and then have another 2 students from China. If you look at the mixed product on the Fock space, then this product is bounded if and only if this function is bounded. So that's very nice. And we can say more. If this function is bounded, the function will be constant. There's no other way for this to be bounded. It has to be, if it's bounded, it has to be constant. And this can only happen in one of the 4 ways over here. Mm-hmm. There are 2 trivial cases. If f is constant, then the hf is 0 and this is 0, so that's obvious. If g is identically 0, that's also trivial. If f is a linear polynomial and g is a non-zero constant, then we can show that this is bounded, the operator is bounded. And the non-trivial case is, again, when f and g are given by this linear exponential functions with some obvious adjustments. So not only we know exactly when this operator will be bounded, when this function is bounded, we know exactly in detail. The proof will use a, you have to generalize the Liouville's theorem to the operator theory context, the Banach space-wide analytic functions, and then plus some other things you can then prove this. So this is the complete result. And the Hankel product thing, we only know the conjecture is false, but we don't really know what the answer is. So again, I want to emphasize that the main reason that you can actually do this for the Fock space is because you have the Liouville's theorem. And when you move away from Toeplitz products, you have to use a more generalized version of the Liouville's theorem. And I'm writing this down over here. Suppose you have a function f from the complex plane to a Banach space, and if this function is entire, meaning that if you have any bounded linear functional on x, then the composition is an ordinary entire function. And if a function like this is bounded in terms of norms, then the function has to be constant. I mean, it's not really constant, it's a constant vector. Using this version of the theorem, then you can do the Hankel product problem and also the mixed product problem. The proof of this is elementary. So once you write it down, you realize, hey, it's easy. So again, that's the end of my talk. I just want to give you a summary. On the Fock space, the Toeplitz product is bounded if and only if this is bounded. That is now known. And for the Hardy space and Bergman space, one direction is true, the other direction is false. For the Hankel product, for Fock space, one direction is true, the other direction is false. For Hardy space, Bergman space, the question is still open. One direction is known, the other direction is open. And for the mixed product on the Fock space, the answer is completely known. And for the Hardy space and the Bergman space, one direction is true and the other direction is still open. So I think this is actually a very good question for the unit disk. By now, people know almost everything about unit disk. There is a huge body of function theory about the Hardy space, but still you cannot answer a question like this. Given all the function theory for the Hardy space, you cannot do this. So, well, it's just now we don't know how to do this. Maybe it's possible, but you need to discover new techniques. Generally speaking, the problems over here I mentioned are relatively easy for the Fock space. They are more difficult for the Hardy space and the Bergman space. Or maybe it's not hard, it's just you have not discovered the right techniques. So if you're lucky, maybe you can find a way to deal with the H2 case. My bet is sooner or later, people will figure out a way to do H2. But for the Bergman space, I genuinely believe it's difficult because there's no function theory. And for the Hardy space, there is a lot of function theory and maybe somehow it's possible. So that's all. Thank you.
Thank you, Kehe, very much. Very nice talk. I do enjoy it. Questions, please.
Hello.
Hi.
Hello, thank you.
Yeah.
I have a brief question.
Yeah.
This form, can you go back to one of your slides? Like that's okay. Like in this case, along the talk, you always are showing this kind of product.
Yeah.
But I don't know what's the relevance of this kind of structures.
Yeah. Yeah, it's first time you see this, of course, you don't really realize what this is all about. Again, a difference like this is really mean oscillation. In the case of the circle, you can define mean oscillation using like an ox on the circle. In the case of the disk, you can define mean oscillation using, say, the Bergman metric disks. This is an invariant version of the mean oscillation. In my book, Operator Theory and Function Spaces, you're going to see a very clear connection between this and the mean oscillation definition. So again, think of this as mean oscillation.
Kehe, you missed wave on second part.
Yeah. Oh yeah. Well, I did not exactly miss it. It's if I assume that G is analytic.
Yes, sure.
Tilde and G is going to be the same. Yes.
Yeah, sure.
Yeah. So this
it seems like right. Looks like the variance of random variables and the covariance. This product.
It's not the variance. The variance is this is the let's see. This is the no. There's a term. Yeah, it is the variance. Yes, in terms of random variables, that's exactly the variance. The tilde is the expectation. It's the mean. Bayesian transform is a mean. It's a average. So when you do this difference, you get the variance. Yes.
Right. And another question, like general question, is like, why was Sarason? Why he was worried about the boundedness of these operators?
Yeah, we talked about this at the beginning. I don't know.
Sorry.
Yeah, I don't know. I mean, I don't know why he was studying this product, but then after the last 2 years, I realized that it's a very precise question. So because he passed away, there's no way to know exactly why. And in the book, when he raised the problem, he did not explain why he was asking this question. He simply asked the question.
Right. Yeah, I'm asking that because I think he also published something on unbounded Toeplitz operators. So yeah, I don't know.
Okay.
Thank you very much.
Sure.
More question, please.
Yo tengo una. I have one.
Yes, Armando.
Yeah.
I understand that for unbounded operators, we need to define the set, the domain. And I don't know if that's trivial, but in all these results, the domain is arbitrary? I know that it must be dense, no? In
all the three cases, the natural domain will be finite linear combinations of the kernel functions.
okay.
That's going to be a dense set, and then all these operators will be defined when the functions are unbounded.
Does it have sense to think in other domain, or to think in other dense domain? Does it have sense?
If I understand your question right, when you say domain, there are two possible meanings over here. I mean, you can certainly look at other domains in the complex plane, and then you study the bug.
No. His question is, if you consider, say, domain of operators like linear combinations of analytic polynomials.
Yeah, certainly. Yeah, the polynomials will be a dense set, but it's easier to use linear combinations of the kernel functions. That's a lot easier to work with.
Okay.
Yeah. So yeah, you can certainly use the polynomials as your domain. That's perfectly fine. But it's a little more difficult to compute usually. The kernel functions are much easier to use.
But nothing will change if you consider that domain.
In any case, I mean, the set of finite linear combinations of kernel functions is always dense. So always do that.
Okay. Thank you.
Yeah.
Questions? More questions or comments?
One question.
Yeah.
Speaking about kernel functions, does the Sarason problem have sense for other spaces, for example, harmonic spaces?
As far as I know, no. Nobody has really studied other spaces. At least I have not seen any results. Yeah, like I mentioned a few moments ago, you can certainly consider this kind of problems on a bounded domain on the complex plane. You can study the Bergman space, the problem will still make sense. But given the fact that even on the disk, for the very classical Hardy space and Bergman space, you cannot do the problem. So I've imagined that if you switch to another space, most likely it's going to be a very difficult question. The Fock space, yeah, for the Fock space on the complex plane, there are some recent generalizations. So we worked on the ordinary Fock space. It is possible to do this for like a weighted Fock space, for certain weighted Fock spaces. And I already seen like 2 or 3 papers in this direction. If you use, say, the Gaussian version we use over here is e to the minus z squared. You can use e to the minus z to the power 4, for example. Ways like that, you can actually do this. And then there are some other ways you can do the Fock space version. But for like Hardy and Bergman space cases, I imagine that it's almost impossible. Before any other attempt, you should try to settle the problem on the disk first.
Kehe, as far as I understand Igor's question, the main ingredient in this problem, first we need to have reproducing kernel Gilbert space. So you have that dense domain, linear combination of kernels. Then you involve Berezin transform, which again defined via reproducing kernel. So this is somehow permits you to state equation for any Hilbert space with reproducing kernel.
It's possible, but then the only thing is if you just have an abstract reproducing kernel Hilbert space, for example, if you just look at the Dirichlet space, then the definition of the Toeplitz operator becomes an issue. Because our way of defining a Toeplitz operator, you like use a projection from an L2 space to a subspace. And for spaces like the Dirichlet space, there's really no natural containing L2 space.
But you may consider, for example, spaces of polyanalytic functions, where everything is.
It's certainly possible. Yeah, it's possible. But again, like I mentioned earlier, it's probably you can raise the problem, but probably there's no hope of getting anything, because already for H2 and A2 on the disk it's impossible. So
no, but for Fock space you can try and polyanalytic.
Yeah, for Fock space on the plane you can definitely try other things. Yes.
Yeah.
Yeah.
I have another question.
Sure.
This is not exactly related, but I want to use the opportunity to ask you. What is the situation with whale operators, whale translations in the harmonic Fock space? Are there some analogs for the harmonic spaces?
I've seen many papers about the harmonic Fock space, but I myself, I've never done anything. So I don't really know what the status is. Yeah, I don't know. I never wrote a single paper about the harmonic Bergman space or the harmonic Fock space. There are techniques that I don't really know, and I don't really know what's going on there.
Okay, thank you.
Yeah.
Any question left? If no, Kehe, let me thank again you for a very nice talk. You are welcome to our seminar whatever time you like.
Thank you. Thank you.
Okay,
Thank
take
you.
care. And
So what is your next book?
Good question. Yeah, I don't know. Yeah.
Okay, bye-bye, Kehe.
Thank you. Bye.
Bye. Thank you very much. Bye-bye, everyone.
And,
Nice seminar.
Maribel,
Yes.
Giovanni, our next